Something that was noticed about chemical substances was that if you put the right substances on a shelf and then put the right complement of substances on a second shelf, that if you ever took a substance from the first shelf, it would react with any of the substances from the second shelf, and vice versa. If you took a substance from the second shelf, it would react with any of the substances from the first shelf. So these two categories are called acids and bases. An acid is something that reacts with a base, and a base is something that reacts with an acid. And it's very useful to have these categories because we can name hundreds of acids and bases, then we can name thousands of reactions. And if we ever discover a new substance and realize that it's an acid, for example, then we will immediately know hundreds of different reactions we can perform by combining it with different bases. Now, there are different kinds of acids and bases. There are different ways that we can set up our shelves, which may include different sets of substances. We are going to content ourselves with the hydrogen theory, which was developed by Svante Arrhenius, a Swedish chemist. And so according to him, an acid, which we call an Arrhenius acid, is a substance which releases hydrogen into solution, the H plus ion, which we'll also refer to as a proton, because if you take the electron away from the hydrogen nucleus, all you're left with is a proton. Svante Arrhenius actually won a Nobel Prize for this theory, so it's pretty important. An example of an Arrhenius acid would be hydrochloric acid. So one of its ions is H+, and when we put it in solution, it dissociates because it's soluble, and so it produces H+ in solution. Another example of an acid is sulfuric acid, H2SO4. Sulfuric acid does something interesting. It dissociates to give away one of its protons, leaving HSO4- as the other ion. And then that HSO4- will give away its proton. And so we will have two protons generated, plus the SO4 2- ion, the sulfate. So we call this a polyprotic acid, whenever we have an acid that gives multiple protons to our solution. Conversely, an Arrhenius base is a substance which releases OH- into aqueous solution. And you might note here that OH- and H+, these are the two parts that make up a water molecule. These will indeed react to produce water. So that's kind of the connection that connects these two substances. And it's what guarantees that we always get reactions when we put them in solution. So an example of an Arrhenius base, something like sodium hydroxide, will give us Na+ ions and OH- ions in solution. And we can also have Arrhenius bases which have multiple OH-, multiple hydroxides that they can donate into the solution. Barium hydroxide here actually does something different than sulfuric acid. It will give away these two OH- at the same time. We won't have to wait to do it in two separate steps. When acids and bases react, they have what's called a neutralization reaction because our acid and base are neutralized. They no longer exist in the solution. The general form for an Arrhenius neutralization reaction is that the hydrogen from the acid and the hydroxide from the base combine together to produce water molecules, and the remaining ions, the negatively charged anion from the acid and the positively charged cation from the base, combine together to produce an ionic compound. And when we have an ionic compound that's produced from an acid-base reaction, we often call it a salt. As an example, let's say that we combine hydrochloric acid with barium hydroxide. So the first thing that we're going to want to do, actually the only thing that we really need to do, is write the balanced equation. And we need to remember the form that we want, is we want the acid and the base to combine together to produce water molecules, and everything else gets shoved together into the salt. So we have hydrochloric acid and barium hydroxide. Now barium is in group 2 in the periodic table. It should have a +2 charge. Hydroxide we know has a -1. So we're going to need 2 of those in the barium hydroxide. Likewise, we will need 2 chlorines if we have the bariums combined together with the chlorines to get barium chloride. And now to balance this, we have 2 chlorines over here. So we're going to need 2 chlorines on the left side. And then now we have a total of 4 hydrogens on the left side and 2 oxygens, whereas we have 2 hydrogens and 1 oxygen on the right side. So we need to double our number of water molecules. And that's it. As long as you recognize that the OHs and the Hs are combining to give you water, then all you have to do is pair these other ions together and balance the equation. The substances we've been considering that produce ions in solution, whether it's the acids or the bases or the soluble salts, are called electrolytes. Electrolytes have the feature that if you add them to water, they will make water conduct electricity. Now, by default, pure water with no ions in it does not conduct electricity. And if you imagine trying to push a current through this pure water, we put some electrons in, and as we dump electrons into the water, then we get a strong negative charge, and that's going to repel any subsequent electrons we try to push in. So we very quickly build up too much charge to get any more electrons into our solution, and the current flow is going to stop. Now, if we have ions in solution, for example, we've dissolved some sodium chloride into our solution, then we have something different occur. Now, the electrons can be neutralized by the flow of these other ions. So, for example, these sodiums could move towards these electrons here, and they could neutralize. And the chlorines could also flow in an opposite direction to offset that increase in charge. And so we have ions in the solution, and that allows the whole solution to have a movement of charge back and forth while remaining neutral. And so then we're not going to have that buildup of negative charge problem that we do with pure water. Now, if our electrolyte can convert completely into ions, so for example, sodium chloride, which we know is soluble, then that means that it's a strong electrolyte, and it would strongly affect the ability of water to conduct electricity. If it doesn't do that, if it only partially converts into ions, then we have what's called a weak electrolyte. An example of that would be acetic acid. So some of the acetic acid will go ahead and dissociate and give away some of its protons, but most of the acetic acid will remain in the undissociated form. A subset of Arrhenius acids, which are strong electrolytes, are called strong acids. There are 7 of those, and we want to actually know all 7 of these kind of by heart. And the reason is because if we know these by heart, we can immediately classify any acid as strong or weak because any other acid is going to be weak. And weak and strong acids have different characteristics in chemistry. Strong bases are the bases which completely react, and there are 8 of these. These are actually pretty easy to remember because they correspond to our alkali metals plus 3 of the alkaline earth metals. And again, if we know these, then we can recognize any base as being either a strong base or a weak base, because if it's not one of the ones that we see here, then it's automatically a weak base. Let's say that we want to write the reaction for barium hydroxide with acetic acid. And we'll go ahead and try and come up with the net ionic equation for this reaction. We can start by doing the molecular equation. And if we recognize all of our charges here, this is our acetate ion, then we can go ahead and make sure we have the correct compounds. So we're going to need 2 of these acetates, our barium acetate. And likewise, we're going to need 2 of these hydroxides for our barium hydroxide. And other than that, looks like we are also going to need 2 of these acetic acids. And if we do that, we should have 2 acetates, 2 acetates. Then we have a remaining 2 hydrogens and 2 hydrogens for 4 hydrogens. So we're going to need 2 water molecules. And that gives us 2 oxygens over here and 2 oxygens over here. And these oxygens and hydrogens I'm just going to consider part of the acetate. That makes balancing it a little bit easier. Now that we have the molecular equation, we can go ahead and write the ionic equation. So the ionic equation, copy down these ions from above. We have 2 of the hydroxides. Our acetate, since our acetic acid, since it's weak, we are not going to break apart the way we did for this barium hydroxide. We're just going to leave it all together. But on the right side, if we check barium acetate is soluble, that's going to be aqueous here. And so we are going to break that apart into ions. And now when we write our net ionic equation, we're going to keep the hydroxide because it produces the water. It doesn't appear on the right side. And actually we're keeping everything here except for our barium 2+. It's the only thing that appears on both the left side and the right side of the preceding equation. In working with acids and bases, a very common technique to determine the concentration of an unknown acid or base is called titration. And what titration is, we have some substance that's our unknown, and it's either an acid or a base, and we will react it with a base or an acid of a concentration that we do know, probably because we have made it ourselves in the laboratory. And we'll see how much of it that we need in order to completely react with all of our unknown. And the reason we're going to know that we've completely reacted with all of it is because we're going to add what's called an indicator. The indicator is going to change color once we reach that neutralization point. Now, a special name for that neutralization point is called the equivalence point. So the equivalence point is where we've added exactly the right quantities so that all of our acid that we started with and all of our base that we added to it has reacted to produce products. And what's special about that is that that means that we can use stoichiometry to convert between the quantity of one to quantity of the other. Let's say that we have a sample of sulfuric acid, that's H2SO4, of unknown concentration. This is a 12 milliliter sample. We'll go ahead and titrate it with potassium hydroxide. We've made this potassium hydroxide in our laboratory, so we know its concentration really well, 0.2000 molar. Now, we'll do this in the presence of an indicator. Phenolphthalein is an indicator which changes to pink as it goes from an acidic solution to a basic solution. And so that will tell us that we've consumed all of our sulfuric acid. And this happens when we've added 8.4 milliliters of our potassium hydroxide. So what was the concentration of our original sulfuric acid sample? Well, we'll start by writing a balanced equation. Now we know acid-base reactions, they're going to produce water as a product, and then the other ions are going to get paired together in the salt. Now sulfate has a -2 charge, and potassium has a +1 charge. So we're going to need 2 potassiums. Now that we have the right compounds, we can balance the equation. So if we have 2 potassiums on the right, we're going to need 2 potassiums on the left. Now if we have two oxygens here, and I'm just going to leave the sulfate oxygens to themselves and balance sulfates. But we have these two oxygens here, other than the oxygens and the sulfates, we're going to need two oxygens there. So we're going to need to double the number of water molecules. And now I have 2 plus 2 is 4 hydrogens, 2 oxygens, 2 oxygens, 2 potassiums, a sulfate, and a sulfate. So that's the balanced reaction. Now we want to go ahead and use this information to convert our knowledge of the known, the potassium hydroxide, into information about our unknown, the sulfuric acid. So we had 8.4 milliliters of our potassium hydroxide that we added, and we knew its concentration was 0.2 moles per liter. So liters cancels, and this works out to 0.00168 moles of potassium hydroxide. All right, well, now we can use our balanced equation here to convert from moles of the hydroxide into moles of the sulfuric acid. So there is a 2-to-1 ratio here, 2 KOHs for each H2SO4. So our moles of KOH times our 2-to-1 ratio. KOH is on the bottom, so it cancels out. This gives us 0.0084 moles of H2SO4. And our last step, we need to convert from moles back into concentration again. So we have our 0.0084 moles of H2SO4. Now remember, this came from a 12 milliliter sample. So here we're going to use that 12 milliliters, or 0.012 liters. And moles over liters gives us concentration, molarity. Works out to 0.7 molar concentration of that original 12 milliliter sample of sulfuric acid.